Example 2 is kind of a classic type problem. It's the first type of problem where we actually have to construct a real model. So why don't we take a look at this and try to construct a model together? So a rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other 3 sides. So when I look at this, I think the word rectangle is super important because that's going to give us the shape of the garden. I think I got to draw a picture. So let's put the rock wall over here. And then we're going to use that as one side of our garden. And then we're going to have 3 other sides. So here's another side. Here's another side. Here's another side. Okay. To illustrate this is a rectangle, I could put sort of these right angle markers on all sides like this. And what I want to do next is I need to introduce some variables. Now, I feel like I don't need to worry about the rock wall side because there's no fencing here. So really, I only have 3 sides I need to worry about. I'm going to call this horizontal piece X. I'm going to call this vertical piece Y. And by virtue of the fact that we have a rectangle, I think that this side should also be Y. So our picture looks like this. Does anybody have any questions about this picture? This picture is obtained by reading that first sentence. So I don't want to over highlight, but the wire fencing for the other 3 sides is what tells you that you have it like this. The fact that it's a rectangle tells you that these 2 sides are the same, and this one's different. Okay. So if we read the next sentence, it says, given 100 feet of wire, determine the dimensions that would create a garden of maximum area. So the first thing that kind of jumps out to me is this maximum area. In other words, we want to maximize area. Okay. That's our goal. And we need to write an equation that represents this area. What do you think the equation that maximizes area is going to be? Someone type the answer in the chat box, please. No response. Okay. Well, the area of a rectangle is given by the length. Yes, I see 2 correct answers. I like Selena's answer. Selena, so this is length times width. And in our case, this is going to be X times Y. And this is a function that has 2 variables. So we usually write sort of as 2 input variables. Right. So I knew what you meant, Aaron, when I read what you wrote in the chat box. I just want to warn you, you got to be a little bit careful. Don't use X to mean multiply because you can confuse yourself really easily. Anyways, typing, it's hard, right? How else are you going to do multiply? But you're correct. The area is the length of the, the area is the product of the 2 sides. Now, somewhere buried in here is a constraint equation. So does anybody see what the constraint equation is? It's buried in the story. I haven't highlighted it yet, but I can tell you, but maybe it's better if you can kind of see. Yes. Excellent, Kenneth. Ken. So I'm going to highlight in orange, I guess. Or I guess I did red, sorry. But when they say this given what, when they say this given 100 feet of wire, they're telling me how much wire I have to use. That's going to be how I'm going to get my constraint equation. So my constraint equation is going to be the sum of the three sides, which is x plus 2y. And that total amount of fencing has to equal to 100. Okay. So once I see that, I can make a substitution. And when I make my substitution, I'm going to get the area is going to be equal to, oh, we have to solve for one of the variables. So I'm going to rewrite this as x is equal to 100 minus 2y. And then I'm going to have 100 minus 2y times y like this. And this is a of y. Does that make sense for everybody? Is there any questions? Okay, great. So then I can simplify this, right? Because I have to take a derivative, so I want to simplify. I'm going to distribute. This becomes 100y minus 2y squared. And that's my area function. So this is what I want to maximize. Okay. So we're doing great. We're in great shape here. I do want to worry about the domain before I do the calculus to this. So when we think about the domain, our function, our values, our independent variable is y. So what do you think the smallest y could be? Anyone have any thoughts? So a lot of times the two endpoints give you what I call degenerate cases. Degenerate means like it's not a normal case. Oh, we have a question. So a student asks, how did we get this formula? So we know that the area is equal to x times y. We have this constraint equation, x is equal to 2y. X plus 2y is equal to 100. I can solve for x, and then I substitute that in for x right there. And then I simplify. Okay. All right. So for me, the smallest that y could be is 0. And that gives you the degenerate case where you just lay the fence right along the wall. And why do I call this a degenerate case? Because that has no area whatsoever. So we're trying to maximize area, but if you let y be 0, you just have a bunch of fence and no area. Does anybody know what the upper bound for y should be? I'll give you a hint. It's another degenerate case. Oh, hold on a second. How did I get the constraint equation? Someone just asked. Oh my God, I thought I just explained this. Okay. You see this statement here? You have 100 feet of wire. So how much wire do we have? We've got y plus x plus y. So we know if we took the sum of the lengths of the three sides, that's going to be 100. That's the constraint equation. It's highlighted in red. Maybe I need to pause here. The questions come in on like a 2-minute delay. Anybody have any other questions? So does anyone want to answer my question? What's the biggest y could be? Can't be infinity because you only have 100 feet of wire. It can't be 100 because you have 2 y's. Can't be 200 because you only have 100 feet of fencing. I think it should be 50. Like I said, it's degenerate. It's like you have one wall like this, one side like this, another side like right next to it, and there's no area. So the domain is not an issue for this question. Like we don't really need to worry about it. But I just wanted you to realize that there is a constraint, and that comes from the fact you have 100 feet of wire. Okay, cool. Now we need to do the calculus part. So we need to maximize this function. I can already tell you that a of 0 is equal to 0 and a of 50 is equal to 0 as well. So we don't have to worry about those 2 endpoints. So what we want to do next is we want to calculate the derivative. So now we want to maximize a of y. And we first need to find the critical values. So when I take the derivative, I'm going to get 100 minus 4y. I want to set that equal to 0. So 0 is equal to 100 minus 4y. This tells me that 4y is equal to 100. This tells me that y is equal to 25. So this is one of our critical values. Okay. At this step, if you were able to recognize that this is a closed interval question, then you could just calculate what a of 25 is. And a of 25 would be 100 times 25 minus 2 times 25 squared. And I think if you pop this into your calculator, you're going to get 1,250 feet squared. So according to the closed interval method, that would be your answer. Now, you could show that this was a maximum. How could you show this is a maximum? One way you could do it is you could use the second derivative test. So if you took a double prime of y, that's going to give you -4. -4 is less than 0. Negative things make you sad. That's a max. Or you could use the first derivative test. You draw a little number line. Here's 25. You plug in a number to the left, you get it increasing. You plug in a number to the right, you get it decreasing. Maybe you do a prime of 20 and a prime of 30. And if you did those test points, you would see that your derivative has the appropriate signs, and then that would help you realize that you're at a maximum. Okay. My feelings, this way is the most mechanical, but finding the endpoints is not so easy, I guess. Hopefully it's easier now that you've seen one example. I think this first derivative test is a good one because this shows it's an absolute max because it's always increasing, then it plateaus at 25, then it's always decreasing to the values greater than 25. This second derivative test only gives you a local maximum. So if you look at this, if you recognize this is an upside down parabola, then the local maximum is the absolute maximum. Is there any questions about this example? I think I just have one more thing to do. I think they ask for the dimensions. So when it says calculate the dimensions, that means you got to give them what the x value and the y value is. So my equation for the x comes from this constraint equation. So what I could do is I could copy this down, and maybe I'll put it right here. And let me, sorry, let me move this down a little bit. Okay. So this is going to be 100 minus 2 times 25. That gives you x equal to 50. So the dimensions are 50 by 25, and the maximum area is 1,250 feet.